It's a true honor to be here. I really learned a lot about how the government research programs work. Thank you, DARPA, for inviting me. So if you want to understand the supply chain in the electronic industry, the key thing to understand is also scale, right? So if you look at the, I kind of show electronic industry in four groups of 40 years ago. It was an IDMs. We were kind of dealing with thousands of units, right? It was all built in IDM in the same place. Everything came from one factory. They had this packaging there. Then, Qualcomm came along 20 years ago and kind of expanded the scale of the industry from thousands of units to millions of units. And with the cell phones, we had to kind of go fabless and started working with fabs and OSATs, but we're still shipping millions of units. But today, with the advent of AI and a few other things I'll show you where we are building a lot of complex systems, it's truly a systems engineering, right? So it's no longer a few chips in a cell phone, for example. We have about 70 different components that all make up the supply chain. So we have to have every single one of them for us to be able to ship the phone. And we are shipping them in billions of units. So that's the other thing that's changed the equation in the supplies. So I want to talk about what are the systems we are building and the system complexity that comes from it, and how the semiconductor landscape that exists today, where are the kind of capacities that exist in the leading edge and packaging and things like that. And a couple of key ideas, not many. It's very hard to solve supply problems, but I'll show you one or two ideas that we have on how we ensure supply resilience. So to start with, I think we had a lot of conversation today about generative AI. There's about 175 billion parameters. Even in our edge implementations, we can get up to 7 billion parameters. So to accommodate this, we have flash and DRAM and a lot of components that have to change to make this fundamentally successful implementation. And I think Bill and Naveen and Mukesh, many others talked about this. I don't want to spend too much time talking about the generative AI. But I think the key is the attention, right? If you look at what makes human beings different from other animals, I can look at a room full of people, but I still kind of know I got 12 minutes left. The attention that you can focus is what makes the human beings different. And bringing that into the transformer architecture kind of helped generate a lot of new applications that's really taking off. And the connectivity is another important piece. Our cell phones today are 5G, but not too long ago, we were doing 3G and 4G, which was primarily used for talk. We kind of went from, hey, are the calls dropping? Can you hear me? To they were more robust and things were functional. So this was in the later years. But as we go to 6G, you're going to have a lot of things-to-things connections. And these all exist in very different bands. So if I take your cell phone to Japan, it might be 3.9 gigahertz. And if you go to Korea, it may be 2.4. And then you come to the United States, it's 1800. For handling all these different bands in every place, you are adding components to your supply system that makes the whole system extremely complex. And if you take an automobile where Qualcomm is putting a lot of effort in, and we have a lot of traction in this space, and here, if you look at a roadside intersection, there is a roadside unit, RSU, that's kind of operating like the expert system. And there is a car with certain chips, and there is a pedestrian with a cell phone in their hands. And all of them can talk to each other, and we use like CV2X protocols to intercept each of these. Today in 5G, with about 6 microsecond latency and the connection density guarantee, you can implement them in smart cities as a safety feature. But if you fast forward to 6G and reduce this to a 2 microsecond, you can actually have the roadside intersection manage the intersection such that nobody has to stop. It's possible because the latency and the connection density and the guarantees will become possible. So a lot of exciting things happening. And in order to put all this together, you can kind of look at the supply needs to be so complex. So I've kind of divided them into 4 groups here. Like the vertical logic technology, I think this everyone talks about. This is kind of like the gate-all-around or the FinFET technology, which have super high capacity, CapEx needed. But if you look at the total number of wafers that Qualcomm buys, we actually buy a lot more in the planar logic and the RF, where we build our power management systems and audio codecs and transceivers in the radio frequency. We also need a lot of passives. We buy inductors, they are sometimes built on the package, sometimes they are surface mount devices, SMDs, and we do capacitors. Some of these capacitors are integrated with the die, some of them on the surface mount devices. So that's what makes up all these 70, 80 components that we need. So if you look at the breakdown of where we get things from, right? I think this everyone knows that there's only 12% of the capacity to build semiconductors in the United States today. I think people from Commerce talked about this before. In the 1990s, it used to be 50, 60% or 70%, and then it came down to 12% now, and the goal of this CHIPS Act is to get back to 50%. But most of this is, it's kind of categorized here as memory, logic, and discrete analog. But here, the important thing I also want to point out, if the total capacity, the trailing nodes, it says is 33%, and the analog and RF power, it says is 16%. So together, that's 50%. So if you look at the world of where wafers are being produced, about 50% of them is in older nodes, right? There's only 14, 15% in the leading edge. I think it's an important point I want you to remember. And if you look at the vertical advanced technology, here it's mostly Qualcomm. We are getting most of our stuff from Korea and Taiwan. And Taiwan is a very significant source. So, this is one of the major concerns for us. If there is a power outage in Taiwan, we lose 10% of the capacity. That's like $4 billion for us and almost $50 billion for the industry. And if there's a flooding in Hsinchu, that's $21 billion. And if there's an earthquake, lo and behold, that's almost $40, $50 billion. So we are extremely sensitive to what happens in a small island, and which is not an ideal state to be in. And so the logic planar technology is the interesting one. So I told you 50% of the worldwide capacity on wafers is in this logic planar or legacy technology. And here, if you think about when these were built 20 years ago, like Intel and a lot of the companies in the United States were in the business of building wafers at that time. And their model was they would build them in 65 nanometer node, and when 45 nanometer node came along, they'll shut that down or move the tools, move them to 45. So there's really no capacity that exists in these nodes because they were migrating them all the time. And as the complex things I showed you in the semiconductor chart in all these industrial automation and AI and all of them grew, we needed these power management and other chips. And guess where the capacity came? Because nobody was willing to put new money into an older technology anywhere other than China. So a lot of this capacity ended up existing in China, and that's where it resides right now. It's one of a big challenge because the center of gravity of the legacy nodes is mostly in China. So, the DARPA team asked me, they want to hear innovative ideas on what we can do. So I put some innovative idea. By the way, the equipment industry doesn't like this idea. So let's say we invest the dollars into a 450 millimeter square wafer technology, which was done, which was all talked about and invested in almost 10, 15 years ago. But let's say we do that today. It's very hard to do that in deep UV. Nobody's going to build a deep UV at 450 millimeter square. But deep 193 is possible, and others are possible. So if we do that, and we can bring back the manufacturing with that investment, but the equipment companies don't like it because they have to invest a lot of dollars into this, and it'll take them 20 years or 15 years to recover the cost. But if there's government investment, that might be an interesting idea to consider. So let's talk about advanced packaging, right? So the advanced, quote unquote, advanced in the advanced packaging is really something that the foundries are kind of cannibalizing the packaging market with, in a way, right? So if you think about it, they want to bring patterning. They want to bring class 1 clean room type operation, which enables new features, but is that the only answer? So if you look at the R&D dollars that has gone into advanced packaging in the last 50 years, Bar Intel. I think Intel has got some innovative things that are cost effective. I really like the EMIB and other approaches that Intel has developed. But if you look at the rest, it's a lot of very expensive technology in a field that we're not sure if that needs to be that expensive. So I'm hoping with this NAPMP and all of the government activities, there is a more multidimensional R&D that enables a lot of cost-effective solutions. In Qualcomm, we would love to use chiplets and we would love to take it, use it, but today it's so expensive, it doesn't make sense, and it doesn't have to be. I think the R&D dollars were not spent in a uniform way to see what other opportunities exist, and I hope with DARPA and the CHIPS Act and others, we're going to make some investments that make this cost effectiveness become reality in the advanced packaging space. Okay, so some ideas, right? I don't have many, but I'll show you a couple of them. Of course, chiplet technology is key, right? And so far, if you look at the last 20, 30 years, we've met our user experience. Qualcomm has shipped a phone every year. And every year, the reason people buy our phone is mainly compute power reduction, right? So we've focused the user experience and battery life improvement coming from compute power improvement. And it's really process technology as, I would say not all of it, probably 20, 30%. Bill said in NVIDIA's case, they only got 2.5x process technology improvement in a span of 12 years. For us, it's probably a bit more, 40%. But what do we do if that's not going to be there? We can substitute it with these connection density improvements. That's part of 3D. Everyone talks about it, chiplets. But to me, I can't use it because it's too expensive. Nobody's going to pay twice the amount for a cell phone and buy it just because I got 3D stacking. So we got to figure out how to keep this thing in a cost-effective manner and how we can do it. I think there are lots of ideas, and I think in the next 2-3 years it's going to happen. So if we do that, then we take away from the leading edge node. Part of the advantage I get is the leading edge nodes are increasing in cost. The gate, forever, Moore's law has said that the cost per gate is going to keep going down, which it was, but in the last 2-3 years, it's turned around and it's going up. So if I don't go to the latest technology, my gates becomes cheaper. I can keep them at an older node and stack them, and I can save some money. And also gives me some flexibility. I can go to different places to build different chips. So that's one idea. But to continue this idea, I want to give you the thought how complicated it's going to be, right? Because on one hand, the process technology itself, the extension of the Moore's law that is shown on the top, is taking a lot of chiplet kind of concepts. There's going to be stacked gates like CFET, which is a vertically stacked N and P transistor, which also uses some stacking technology. Then there is backside power, which uses some kind of stacking technology. So how am I going to make that live with the regular chiplet technology that also talks about stacking, right? So it's not very easy. So these two axes somehow have to marry with each other and be very cost effective for me to actually take advantage of them and use it. So the other strategy that we've used is what we call multi-source the same chip. So, in fact, the Qualcomm became a leading fabless company mainly because we were able to, as a fabless, get multiple sources to do our chips, right? So, there were people in the 2010, 2012 who thought fablesses cannot grow to be a very large size because they will be very supply constrained. But we innovated and broke that paradigm by shipping our dies to different factories. We take the same GDS and we can manufacture at almost 6 different foundries and 12 different factories. So there's a lot of innovation that goes into it, how to make this happen, how to get the foundries to match, and how to do this right. So we can do this in the legacy nodes. But when you come to kind of the mid-range early FinFET nodes, we do what's called co-timing. We keep the same GDS, same floor plan, but we time it with 2 different timing models, and then we do ECOs to make sure they're going to function. And then if you go to the very latest node, gate-all-around, there's no way to do anything like this. So we just kind of pick the one or ping pong with each other. That's how we multi-source and ensure our supply resilience. So in summary, supply resilience is got to be a core aspect of how you think about your chips. If you want to do the latest and greatest and all the features, you may not be able to keep the supply resilient. So at Qualcomm, scale is a fundamental DNA. So we always, when we pick our choices and how we do things and whether we do chiplets or not, we always think about what kind of scale we can do. And the multi-sourcing is possible, and the chiplet technology offers some advantages here. But we try to maintain a balance. We kind of look at our market, how much we sell in each geography, and source from that geography to a same extent. But it's still not everything can be solved. So supply is more complex than PPAC. Thank you very much.